So today I will talk about our recent work on angular momentum densities inside a quark dressed with a gluon. This work is done in collaboration with Ravi Singh, myself, Professor Asmita Mukherjee, and Professor Nilmani Mathur. So first, I will briefly introduce the different decomposition of angular momentum of a nucleon. Then I will discuss our work methodology, followed by some result, and after that I'll conclude my talk. So polarized deep inelastic scattering experiments have established that 1/3 of the nucleon spin is coming from the quark's intrinsic spin. And the Rake spin experiment have also suggested that the contribution of gluon's helicity to the proton spin is too small to resolve the spin crisis. Now these observations tell us that the protons have orbital angular momentum, and also the light quarks being confined within a range of 1 femtometer. Heisenberg uncertainty principle tell us that their motion is highly relativistic. So the orbital motion of the light quark should have an important role to play in the spin budget of a nucleon. So future experiments like JLab 12GV and the electron-ion collider will provide valuable inputs on the orbital angular momentum contribution of quarks and gluons. But on the theory side, we do not have decomposition of nucleon spin precisely. For a long time, it was believed that the total angular momentum of gluons cannot be separated into intrinsic and the orbital part in a gauge invariant way. But experiments like polarized electron-proton and proton-proton scattering, people are measuring helicity distribution of gluon in a nucleon. But so something can be measured in an experiment should not change under gauge transformation. So what is happening here is that this quantity coincides with a gauge non-invariant gluon spin in a particular gauge called the light front gauge. Later it was shown that gauge invariant decomposition of gluon angular momentum is possible, and Chen et al. Proposed their decomposition. And in that decomposition, they separate the gauge field into two parts, the pure part and the physical part. Pure part is responsible for the gauge symmetry and transforms accordingly, and the physical part contains the polarization vectors, which does not change under gauge transformation. The Chen et al. Decomposition separates the total angular momentum of quark and gluon into spin and orbital angular momentum contributions. It is gauge invariant, but it also contains non-local terms, and only the operators related to the spin and the angular momentum of quark satisfy the SU2 algebra. Later, Wakamatsu proposed another decomposition based upon the idea of Chen et al., and in his decomposition he added an extra term to the orbital angular momentum of gluon. Now this extra term is called the potential angular momentum. Being gauge invariant, this term can be equally added to the orbital angular momentum of quarks. So gauge invariance does not provide us a unique decomposition of nucleon spin. So later Wakamatsu provided a covariant version of the Chen et al. Decomposition, for which the energy momentum tensor and the generalized angular momentum tensor is shown here. He also provided another decomposition which we call the gauge invariant kinetic decomposition, which is similar to G's decomposition, as we will see. Then and these are the corresponding tensors. And next we have the canonical decomposition or the Jaffe-Manohar decomposition, which we get by using Noether's theorem. This decomposition also separates the total angular momentum of quarks and gluons into spin and orbital angular momentum parts, but it is not gauge invariant, and only the operators related to the orbital angular momentum and spin of quarks satisfy the SU2 algebra. Okay. So next we have a gauge invariant decomposition, the Belling-Pfanther decomposition, which separates the total angular momentum into parts, into two parts, which is total angular momentum of quarks and gluons. And none of the operators satisfy the SU2 algebra. And lastly, we have G's decomposition, which separates the total angular momentum of quarks into spin and the orbital angular momentum parts. Okay. And this is the table which summarizes all the different properties of the angular momentum operators. Okay, so different decomposition of angular momentum give the same expression for the total angular momentum at integrated level, because they differ from each other by a surface term. But this is not true at density level. It has been shown in this reference that the kinetic total angular momentum tensor is not equal to the Belinfante total angular momentum tensor unless we add this surface term. So we need to consider the contribution coming from this surface term. Otherwise, we cannot interpret the total angular momentum density as a sum of orbital angular momentum and spin density only. And at this point, it becomes interesting to investigate the orbital angular momentum and spin of quarks and gluons at density level for different decompositions of angular momentum and see how they are affected. So we know that the generalized pattern distributions contain information about the spatial distribution of quarks and gluons. So it is conceivable that GPDs will also contain information about the spatial distribution of angular momentum of quarks and gluons. How this information is encoded was investigated by Polyakov, but it required the nucleon to be infinitely massive in order to avoid the relativistic corrections. But this infinite mass assumption can be relaxed if we choose to work in the light front framework. The Galilean nature of the boost operators allow us to define two-dimensional distribution in this framework which are free from relativistic corrections. So in this work, we have investigated different decompositions of angular momentum and their contribution to the intrinsic spin and orbital angular momentum distribution for a relativistic spin-half composite state of a quark dressed with a gluon at one loop in QCD. So next our work methodology. So we are working in the light front coordinates. So where x plus is the light front time, x minus and x perp are longitudinal transverse components respectively. Similarly, we can define the light front 4 momentum, but p plus is the longitudinal momentum, p minus and p perp are energy and transverse momentum respectively. We are working in a frame where the longitudinal momentum transfer and the average momentum of the system is 0, R0. And these are the expressions we have used to calculate the longitudinal component of impact parameter distribution of orbital angular momentum, spin, and the Belinfante improved total angular momentum distribution. Okay, so as we have discussed that we need to take into account the contribution coming from these surface terms, and this is the corresponding expression in the distribution form. So in order to calculate these different distributions, we need to calculate Fourier transform of different densities, and in order to do that, we have considered a Gaussian wave packet state confined in the transverse momentum space with definite longitudinal momentum, where sigma is the width of the Gaussian wave packet. And in order to calculate the matrix element of different densities, we have considered a relativistic spin-half state of a quark dressed with a gluon at one loop in QCD. And this can be thought of as a perturbative model with a gluonic degree of freedom. The dressed quark state can be expanded in Fock space in terms of multi-parton light front wave functions, which can be calculated using light front Hamiltonian perturbation theory. And these light front wave functions contain the full quark-gluon interaction. The Galilean subgroup of the Poincare group allow us to write these light front wave functions in a boost invariant way in terms of relative momenta. So up to 2 particle sector, this is our dressed quark state where psi1 is the normalization and psi2 is the probability of finding a quark and gluon with momentum and helicity k1, k2 and lambda 1, lambda 2 respectively. This psi2 can be calculated from this eigenvalue equation where H is the light front QCD Hamiltonian. So this is the expression for the 2 particle boost invariant 2 particle light front wave function written in terms of relative momenta coordinates. So this expression is independent of the momentum of the composite system. Okay, so in gauge theory, we eliminate the unphysical degrees of freedom by choosing a certain gauge, and in light front coordinates, we do so by choosing the light front gauge. And in this framework, the quark fields decompose as psi plus and psi minus with suitable choice of the projection operators. Here the psi minus and the longitudinal component of the field are constrained fields, and they can be eliminated by these constraint equations. So we have only the psi plus and the transverse gauge fields as the independent dynamical degrees of freedom. And we can also choose a specific representation of the gamma matrices in which the 4-component quark field reduces to 2-component fields. And these are the expression for the 2-component quark fields and the dynamical gluon field. Okay, now discuss some results. So in this work, we have taken only the quark part of the energy momentum tensor. Now, if we look at the kinetic energy momentum tensor, the second part corresponds to the potential term, and at one loop level in a rest quark state, we have found the matrix element of this term to be 0. So the rest of the operator simply coincides with the canonical energy momentum tensor. This potential term is also found to be 0 for an electron in QED at one loop level. So next, if we consider the gauge invariant canonical energy momentum tensor, since we are working in the light front gauge where the physical part of the gauge field coincide with the whole gauge field, total gauge potential. So here also this T plus K GIC is coincide with the canonical energy momentum tensor, and the gauge invariant kinetic decomposition of energy momentum tensor is same as the kinetic energy momentum tensor. Okay, so these are some results. So these are the result of longitudinal component of orbital angular momentum distribution and the intrinsic spin distribution, where lambda is the ultraviolet cutoff on the transverse momentum, and this is the result for the Bedangadas improved total angular momentum distribution, and this is the expression for the superpotential term. Okay, so instead of taking a symmetric energy momentum tensor, if we take a general asymmetric energy momentum tensor whose antisymmetric part is related to the divergence of the spin density operator, then for such an energy momentum tensor, the matrix element for a spin half system contains an extra form factor apart from the 4 form factor A, B, C and C bar. And we can parameterize the matrix element of the quark spin density in terms of axial vector and the pseudo-scalar vector. So the form factor, so the related to the antisymmetric part of the energy momentum tensor is the axial vector form factor. And we have used this relation to calculate this, extract this form factor, and this is the result. So here we have plotted the longitudinal angular momentum distribution of quarks as a function of impact parameter. On the left panel shows the total kinetic angular momentum as a sum of spin and the orbital angular momentum, and on the right panel it shows the total kinetic angular momentum as a sum of Bedangadas plus the correction term. From the left panel, we see that the spin contribution dominates over the orbital angular momentum contribution. This result is similar for an analysis done for the proton using basis light front quantization, where they have considered the valence sector light front wave function for the proton. And from the right panel, we see that the correction term is positive for this region, which is different from this result, where they have done a similar analysis using a scalar Dirac model, and in their case this correction term has both positive and negative regions. So since we are using only the quark part of the energy momentum tensor, so the quantities we are calculating are scale dependent, and in our case the scale this dependent comes on the transverse momentum as UV cutoff. So these are the plots as we change the lambda, and we can see that this Bedangadas total angular momentum distribution shows significant variation as we change the scale. And these are the plots showing the dependence of the width of the Gaussian wave packet, and we can see that as we increase the width of the Gaussian, the peak of the distribution shifts towards higher values of the impact parameter. And this is the result for this is the plot for the axial vector form factor as a function of square of the momentum transfer, and this behavior is similar to other model based and the lattice calculations. So in conclusion, we have calculated spatial distributions of angular momentum for different decompositions for relativistic spin-off state, namely the quark dressed with a gluon. And we have also calculated the D form factor, which is related to the antisymmetric part of the energy momentum tensor. We have calculated the superpotential term, which is responsible for the disparity between the G and Belinfant the decomposition. The potential angular momentum we have also calculated, and we have found it to be 0 at one loop level. And we have also seen that the Wakamatsu and the Chen et al. Decomposition give the same result as the G and Zaffe Manohar, since we are working in the light front gauge. And in this work, we have taken only the quark part of the energy momentum tensor, and we are calculating the gluon part contribution to these observables. Thank you.
The value of GA at Q equal to 0, Q square equal to 0?
It's at 0 is 0.36.
Oh, okay, it's already there. Thank you.
Do you have plans for improving your model? There are some things that needs to be done, or you think it's complete?
Actually, yeah, we can improve the model, but already these calculations are pretty complicated, but it will be more complicated. But definitely we can improve the model.
And do you know in which direction and what can be improved?
Yeah, we can add some, for example, an anti-quark to this system.
Thank you.